So complex numbers consist of two parts, a real part and an imaginary part, and we typically write them then as z, a complex number, is equal to a plus jb. Because there's two parts, it requires a complete plane to represent them graphically. A real number we can show on the real number line, an imaginary number we can show along an imaginary number line, but when we've got both a real and an imaginary part, we form what is known as the complex plane, where the horizontal axis of the plane is referred to as the real axis, and we plot the real value of the complex number along the horizontal axis. The vertical axis becomes the imaginary axis, where we plot the imaginary part of our complex number. So for example, here we have z is equal to 2 plus j. We come over 2 units along the real part, because in this case a, the real part is 2, and we go up 1 unit along the imaginary axis, because our imaginary part is 1 times j. So here we would have 1j, 2j, 3j. You can think of j almost as a unit vector, or a quantity showing us which axis we're on. The distance along this axis is 2, the distance along this axis is 1 times j. Alrighty. We here are representing this real number, or this complex number, in what is known as rectangular coordinates, a horizontal value and a vertical value. As you know, we can also represent points in a plane using polar coordinates, where the two coordinate values are an angle of rotation away from the horizontal axis, which we call theta, and the distance from the origin out to the point along that ray is known as the magnitude of the complex number. So we can write z in polar form in terms of this magnitude and an angle. Now, how do the polar and rectangular coordinates relate to each other? We can go from rectangular to polar using Pythagorean's theorem. So from rectangular to polar, we can calculate the magnitude of z. That's simply equal to, using Pythagorean's theorem, the square root of the two sides. Well, this is a, so it would be the square root of a squared, and the distance along the imaginary axis is b, so a squared plus b squared. And theta, the angle, is equal to the inverse tangent of the opposite over the adjacent, or the inverse of the imaginary over the real, or the inverse tangent of b over a. Now, to go from polar coordinates back to rectangular coordinates, we again use the right triangle and recognize that the distance along the horizontal axis is a. That's simply equal to the projection of that point down onto the real axis, which of course is the magnitude of z times the cosine of the angle. So a then is equal to the magnitude of z times the cosine of the angle theta. And b, the imaginary component, is equal to the magnitude of z times the sine of theta. Again, it's the projection of this point onto the imaginary axis. So that takes us from polar coordinates back to rectangular coordinates. Now let's just do an example real quick to show how this works. In fact, let's do it for this quantity right there. The complex number z equals 2 plus j, given to us in rectangular coordinates. How do we get the polar representation of it? Well, coming down here, the magnitude of z is going to equal the square root of the real part squared, which is 2 squared, plus the imaginary part. Well, the imaginary part is coming up here 1 unit. Again, we don't square the j. The distance there for the geometry in this circuit, in this problem, the distance there is 1 unit, so it'll be 1 squared, and that equals the square root of 5. Theta is equal to the arctangent of the imaginary part, which is 1. It's not j, it's 1. Again, this distance is 1 unit, so it'll be 1 imaginary part over the real part, 2, and that turns out to be 26.6 degrees. Now to show how we take it and go back, well, first of all, this number then in polar coordinates we would represent as square root of 5 angle 26.6 degrees. Okay. Now, how do we take this number in polar form and go back into rectangular coordinates? Well, it tells us right here that a, the real part of our number, is equal to the magnitude of z, which we found to be the square root of 5, times the cosine of the angle, which is, in this case is 26.6 degrees. When you're doing this, make sure you've got your calculator set in degrees and not radians if you're working in degrees. And that then, of course, is going to equal a, the distance along the real axis, which we know, and when you do that calculation, you find that is equal to 2. And b, the imaginary part, then, is equal to the square root of 5 times the sine of 26.6 degrees, which equals 1.